The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening, everyone. Welcome to the webinar on Towards AI Native 6G Networks. I am Leah Yuan, your moderator today, and I am a research engineer in ZTE Corporation and also Working Group 3 Chair of ITUT Autonomous Network Focus Group. And it's my great pleasure and honor to moderate today's session. To realize the vision of ubiquitous intelligence connectivity, AI native networks has become an important research direction for next generation communications. It will enable deep integration of networks and AI, efficiently coordinating connection, data, computing power, models, and knowledge resources within network to support AI workflows in a native way. This will empower networks with higher level autonomy and facilitate digital and intelligent transformation across all the industries. We have gathered top experts today who will deliver insights into the latest advancements, key technologies, and application scenarios of AI native networks from both technical and application perspectives. So our first speaker today is Dr. Xiaofeng Liu. Dr. Xiaofeng Liu is Deputy Chief Engineer of Mobile Communication Invention Center of CEICT. He received his PhD in Communications and Information Systems from Beijing University of Post and Telecommunication. And he is now the Deputy Chief Engineer of Mobile Communication Innovation Center of China Academy of Information and Communication Technology, the professor level senior engineer. He is also serving as the chair of IMT 2020 Promotion Group 5G and AI Working Group. His current research focus is on integration of wireless communication and AI. And today, his topic will be overviews on integration of 6G and AI. Let me hand over the stage to our first speaker, Dr. Liu, to start us off with his presentation. Dr. Liu, over to you.
Okay, thank you, Chair, and really honor for me to have a chance to introduce our views from the AICT for the integration of 6G and AI. And I will start with my PPT right now. Okay. This is Xiaofeng from CICT, and great honor for me to share some views on integration of 6G and AI from industrial side. Can you hear me?
Yes, we can hear you. Yeah.
Okay, thank you. And let me start. With the fast development of AI technology, and it has caused a revolution covering almost all vertical industry. Also, for wireless communication, great attentions have been paid for academic research, and huge numbers of papers have been published to investigate AI-based new technologies to improve the performance of telecommunication network. Accordingly, for different standard organizations, enhancement of different network with AI technologies become the hottest topic. Also for 3GPP or release 18, I think it is well recognized that AI-based air interface will become key component for both 5G Advanced and 6G. And in general, I have seen that the integration of wireless and AI will bring fundamental change to wireless communication system design. However, from our side, we also think that in order to use AI-based solution properly to construct the next generation network, there are still lots of challenges worth of our further study and should carefully considered. From the experience of existing study, at least from 5G Advanced, the following 4 challenges are well identified. They are balance of performance and efficiency, high quality dataset construction, model monitoring and management, distribution and effective use of computing resources. From the point of system design, efficiency is of the most importance. This means that even if we could prove AI-based solution to achieve some performance gain, the real cost of achieving such gain needs to be carefully estimated and evaluated. In order to achieve gain efficiently, we have to take care of high-quality data site construction, model monitoring and management, distribution and effective use of computing resources. All these challenges are applicable for all AI-based design. In these slides, we show that our standing AI will enable a new intelligent dimension for wireless system communication system, which is parallel to time, frequency, and spatial demand. In order to explore the new dimension, big data, computing resource, and AI technology are the key elements should be studied together. It should be noted that intelligent dimension as a new resource. Physics is data. AI model could be recognized as tools, and the computing resources are hardware basis. If we want to increase the efficiency of AI-based solutions, there might be several methods. I think the most popular thinking is that we use powerful AI model with good generation performance. However, in order to train an AI model with good generation performance, especially for complex wireless system, it requires a lot of data covering variety of scenarios and system configurations, which in turn will cost huge computing resource. On the contrary, some small model with a simple structure trained by small dataset also perform well for some specific scenarios and has its own room for real deployment. Therefore, although design of an AI model is rather a state of art and not easy to be fixed or specified. Therefore, we could not follow a simple way or rules to make AI-based design. Inclusive design allowing multiple schemes is quite essential. And this slide show the conventional, theoretical show our thinking about what the key tools for AI-based enhancement. For typical AI technologies, there are different areas such as computer vision, speech recognition, natural language processing, etc. We observe that machine learning is the main tools enhance the performance of various network. With different machine learning algorithms like supervised learning, reinforcement learning, some NP-hard problems could not be solved to improve the 5G and 6G system performance or efficient. We are now in the period of solution of AI technologies. With the emergence of ChatGPT, we have entered a new era. And now we try to have a close eye on the design and use cases of big model. Many discussions have happened on the possibility of introduce model to various systems. We can see ChatGPT belongs to the field of natural language reprocessing, namely NLP part, and it's hard to be directly used in various system design. However, there's still some chance that 6G or next generation network develops its own big model. However, for various systems, there's clear computing resource limitation at both UE and GNB side. Training of big model at either UE or GNB side is not realistic. It is more likely that bigger model is trained in cloud and is transferred or delivered to different components for inference. Some fine tuning should also be considered at local. In order to enable AI-based wireless technologies in real deployment, not only paperwork, some key elements should be kept in mind, like use case, site, algorithm, simulation methodologies, verification tools, and so on. All these elements are essential and interact with each other. For example, if we want to deploy an AI-based feature, like AI-based management or positioning, we will have to think about how to construct the training dataset and the related progress for data collection. Then simulation tools and the simulation methodologies according to the dataset construction should also be developed for model training and performance justification. Some reference AI models could be used for the performance justification. Well, for the real deployment, the actual AI model could be different. In parallel with simulation performance justification, some verification tools and methods for real product should also be developed. And the developed tools should be for testing. When the performance is identified and cost is within a reasonable range, the identified use case would be considered to be specified, as shown in the picture in these slides. And we think that for a fully specified feature, whether it could be used in real product or not, still needs more consensus building. This progress should be among different vendors. And after some consensus building, milestone will be established and the timeline should be ready for the different vendors. It normally achieved pro release, just like if we want to really use like a feature and then we have to realize it maybe at the end of a release. It's like right now we have to make the specification work for release 18, and then if you really want that feature, and then maybe after 2 or 3 years, and the vendors have to develop the tools. And after the system tests, including the interoperability and scale network test, AI-based feature could be deployed in real network. And this 8 process is really essential for develop the AI-based network, also for the technologies. These slides show some special use cases, maybe also a candidate use case for the 6D native design. And I think that in general, the use case specified in 5D, that's like in 5D advanced right now, to be support default. And there's still some room for the new use case. Maybe after intensive study, we still have more chance to introduce more use cases. In 5D advanced, 3 representative use cases have been started. And according to the discussion right now, 2 of them might be specified in next release, just like release 19. Here, I think I should have shown many use cases here. And the first one is the AI-based CI/CD compression. And we have selected the AI-based CI/CD feedback as a really important topic for wireless computation AI competition. And we observed that higher channel feedback accuracy with less feedback is achieved by using AI model to replace the legacy 5G NR scheme. We also found that transformer-based AI model achieve very excellent performance. Special frequency domain CIS compression feedback is selected as the representative use case for study in this 18. The many companies are also interested in the joint design of temporal, spatial, and frequency domain set feedback. During the study, we see that some new training types, like separate training, retraining, are proposed to avoid direct AI model transfer among different entities. It should be noted that CSF compression is the only two-side model case in 5G Advanced. Honestly, this is really complicated use case for real deployment. And even after one release study, it is not convinced by many companies that we might need a continued study in next release. And I think the main reasons for not that this use case is not proposed for for the next stage normative work, it may maybe have two main reasons. The first one may be the trade-off between the performance and the complexity or overhead, as I have listed in the first slide, and that the balance between the performance and overhead. And then the second reason is the issues related to the inter-vendor training collaborations. Because we want to train a model, we have to align between different entities, just like UE and G-Node-B. If we transfer some data between the different entities, then how to align the data and how to align the model still needs more discussion. And such discussion maybe not happy to each vendors, and then according to the conclusion, it may be we should have to wait more time and need more evidence to make more progress to have more promote for that use case. And the next use case may be AI-based beam management. Beam management is an important design for high frequency coverage and throughput enhancement. With AI algorithm, partial beam pair information could be used for full beam pair estimation. Measurements and the beam pairing time could be reduced with AI-based solutions. And during the discussion, some companies also proposed the time domain AI ML-based solution could be used. And this use case could be, I think, have achieved most companies' support, and it will be entered for the next stage. The third use case may be the AI-based positioning. AI-based positioning solution could improve the positioning accuracies in typical n-loss scenarios. There are different algorithms to enhance the performance of AI-based positioning, like direct AI positioning or AI assistant positioning. Now, the discussion on AI positioning are more focused on partial labeling dataset or generation performance of AI models. Also, of beam management and the positioning has been proposed to specified in next release, and the complete specification support this two use case is expected to be published in middle of 2025. After specification ready, it is still reluctant to say these two use case will be deployed in commercial network. It may be some reason. I think that these two use case are not deployed in commercial network yet. With the addition of AI, it is not enough to drive operators to use these two features. Therefore, from the valuable experience in the study on AI for NR in release 18, we have to say even more use cases are specified in 6G. There are still a long way to real use them, and we should take really careful on the real value of AI technologies and convince all the operators to use them. I think another very interesting use case that is in the fourth box is the AI-based channel estimation. AI-based channel estimation have already show a excellent performance under different scenarios with quite limited overhead. Especially AI ML-based will be used very excellent network at very low SNR regions to improve the performance of channel estimation. Potential of AI ML based channel estimation had been justified also in the second wireless AI competition we have held already in 2 years before. I think at the very beginning of release 18, AI-based channel estimation is also proposed by many companies. However, at the last moment, this use case was not successfully selected. It might not easy to provide directly reason at why channel estimation is not chosen, even with a really clear thing. Maybe to our understanding, ground truth values for model training is a key factor. From the point of simulation or performance justification, it's easy to achieve the ground truth value for channel character. However, for real deployment, it's almost not possible to achieve the real value of channel variance. Therefore, the key point will be the generalization. Namely, even we can achieve an excellent performance in lab, actual performance in the field will be poor. As for if AI-based channel estimation could be specified and used in safety, I think it is still open. We can expect that flexible reference signal design to enable AI-based solution to show its capability. In the last box, and I think that there's some other use cases such as channel prediction, mobility scheduling, modulation, and so on. All these use cases have the potential to be specified or used in 6G. It should note that for some one-side model use case, in which the AI model is deployed at either UE or DNB side, it could be utilized by specification transparent way. It means that even without any specification, if vendor really want to use that, and they can use that, but it cannot with the help from the other side. That's like if UE want to deploy the AI-based feature, and it can directly use it, but the help from node B, you have to have some specification works and get some signaling from the other side. This slide shows the main specification progress in 3BP for 5G advanced stage. Although we are now in the time of 5G advanced, I think the 3BP has begun to construct the AI-based system for 6G already, especially with the approval of study on AI/ML for NR Express projects. 3GP international standard has opened the door to the various OI already. And following the study in release 18, some typical use case will be specified in next release, means next release 19, such as management and positioning, as I mentioned before. And the study work will continue in release 19, including CSI feedback and AI-based mobility. In addition to specification works for various AI/ML-based enhancement for next generation run and for NG run and core network operate in parallel. Obviously, AI has demonstrated the ability to comprehensively enhancement to legacy networks. And it is a traditional tradition in 3BP that for any important new features, study should begin in advance at least 2 releases to make the whole industry have a full understanding for the new technologies. For example, for the study of massive MIMO, and it has started in 4G, maybe in the period of 4G advanced, and then the product supporting massive MIMO is launched in 5G period. And whereas AI maybe situation may be quite the same, And I think wireless AI is a really historical level new technologies for wireless system, and longer study period is essential. And this slide also provides some important conclusions from the study of AI-based AI for NRR interface. And first one, I think the important concept is collaboration level. And there's already 3 different collaboration level are identified in the study, namely level X, Y, and Z. For collaboration level X, no collaboration is required between UE and G-node B. And for collaboration level Y, signaling-based collaboration without model transfer is required. And for level Z, all use cases require signaling-based collaboration with model transfer belonging to this level. And during the discussion, some sub-level also proposed at sub-level for level Z could also be used for further differentiate the model assumption at UE or network set. I think it's clear that use cases belonging to collaboration level X could be realized without explicitly specification works, just like mentioned before. And maybe some use case without any specification works and will be used even in near future, just like UE could use some AI-based features, because I think that at UE it already use AI chipset already, and if they really want to use it, it can be direct use it and without any specification works. And for 6G, and it also we can also expect some features could be used without any specification support. Second important concept is life cycle management, and also many times we call it LCM. And LCM is really important part for release 18 study. We can see LCM is a collective concept. It covers the progress of data collection, model training, model of functionality identification, and many parts. And we could note that functionality here we see a new name may be the functionality, not a model only. I think the reason is that for the system want to use the functionality at the level of functionality, not only at the level of model. And the last important part is the next important concept is about the model training, especially for the two-side model training. Considering the limitation of model transfer between different vendors, 3 types of training, three main training types are proposed. And type 3, self-training at network and UE side with dataset exchange are proposed. Similar with the concept of federal learning, type 2 joint training with intermediate data transfer are also proposed. Comparing with the pros and cons for different training types, all training types should all be considered for different development scenarios. And in general, from the study of release 18, we can see even AI is only used for some specific enhancement. It will cause lots of study and specification works.
You have 1 minute left.
Okay, and this slide shows some forecast for the future design of 6G. And I think that the main part is that release 18 have established a basic framework for the 6G, and LCM part maybe the basic system structure design. And in addition to that, and some feature design should be on the top of that of LCM. And then per release, specification works and the enhancement for different parts could be involved. This is the summary for the for my lecture, and we think that it's really important for us to begin the study of AI native design, and we hope AI-based design will introduce revolution to the next to the development of whole industry and open a bright future. And that's all. Thank you.
Thank you so much, Dr. Liu, for the overviews on the background and all the progress of integration of 6G and AI. And let's see if any questions from the floor. It seems now maybe we can wait till the final Q&A of the session before the end of the session. So next, let's hand over to our next speaker, Dr. Marona Deba, who is the Chief Researcher at Technology Innovation Institute in the United Arab Emirates. As a world-renowned researcher and expert in wireless communication, AI, and 6G, Dr. Deba will elaborate on why now is the time for telecom GPT. Dr. Deba, the floor is yours.
Okay, thank you for the introduction. So, I'm
Just
Professor.
very quickly jump in. Sorry, Marwan. Could you go to your full presentation screen? We can still see the slides on the left-hand side.
Full presentation screen. It's not full?
Mode. No, it's not on. It's not on full presentation mode.
Okay, and now?
No.
Okay, stop sharing. Let me just check. And
Sure. Thank you.
Sharing. Okay. Is there optimized to video clip? Okay, and now is it full screen?
No, we can still see the main slides, but there's still the slides on the left. And when you go to this, we can see the notes.
Notes.
Yeah, maybe I can share the screen for you if it's needed. Dr. Deba?
Let me just test still one thing, and if not, then of course you'd better your share. Yeah, definitely. So advanced PowerPoint. Yeah, maybe share it because I don't know why it's not sharing the correct. I mean, when I put it, it's full screen. Okay, so maybe you can share it.
Yeah, I can see that, Leo.
So that's on my slides, but
Oh.
it's a good PDF. I don't know what it
Yes.
is.
Sorry, please wait for a moment.
No problem.
Let me find it. I opened so many windows.
Yeah, no problem.
Okay, this is the correct one, I think. Yeah,
Okay,
is this full screen?
Perfect.
Yes. Okay, so as I was saying, so my talk is going to be about a new topic which is related to what we call large language models. And large language models, I think many of you have heard about them, and especially with one of the things which came up last year related to what we call ChatGPT. So it's at the heart of a lot of what we call the Gen AI aspects. And the question here is about using, of course, generative AI today in terms of a foundational model which could help basically in several aspects in the development of 6G. So my name is Marwan Deba. I'm director of the Khalifa University 6G Center, and I'll be giving you a bit of an overview of what we've been doing in the last 3 years on the topic of generative AI and how now we're trying to push it for basically the telecom industry, in which we think that we need to develop an alliance, and I think the ITU here is very well positioned for that, around basically different companies trying to share their data so that we can build an open source model related to the telecom industry on which, of course, verticals within our industry could fine tune that for their own business around that. Next slide, please. Okay. Next slide again, please. I think we can skip this one for the time we have. Okay, so I think many of you are aware, of course, of the big changes that we've been going through in the last years. And one of the big change which has been taking place is, of course, the compute. The compute basically has drastically changed, and I think you've been hearing on the press today how much companies like NVIDIA are getting such a monopolistic, I would say, kind of position today related to the use and need of GPUs around the world. And I think this has been going on basically with what we call CPU-based computing, with basically things like Deep Blue, Watson, to GPU-based computing with basically what we saw with AlphaGo around the year 2016. And recently, with the era of what we call supercomputer or what we call HPC/AI. And one of the things which is very interesting with the supercomputing techniques today is that, of course, they're providing us the capability of constructing or building huge models. And these huge models, compared to the classical machine learning techniques that were presented before by my colleague, instead of solving one specific task, are able basically to solve many tasks at the same time. So they're not tailored to one basically kind of utility function, but basically solving many. And at the same time, they have what we call generalization capabilities, or basically being able to solve unseen tasks. To give you an example, you train a model basically to be good in addition, it will become extremely good in addition. You train a model to become good in multiplication, it will be good in multiplication. But these large language model, they have some specific feature is that if you train a model with data of addition and data of multiplication, you will be able to learn on how to do a division or a subtraction based on these things. And so it can solve basically some tasks on which you had not basically tuned or optimized the system for. And this changes drastically the system that we saw of people constructing AI techniques in the telecom domain with autoencoders, for example, approaches where they were trained for a very specific task. And whenever you departed from that task, the model could not fit in. Next slide, please. And so in the last, I would say, 1.5 years, there's been a big disruption related to a topic called generative AI, which is a subtopic of basically machine learning techniques. And what we've been seeing is, of course, models being able to predict the next word, the next sentence, the next image, the next video, the next sound. And this has come up with a couple of big names that you've been seeing on the press related to GPT-3, to Llama, GPT-4, Falcon quite recently. Falcon is a model, an open source model that we developed within my institution here called the Technology Innovation Institute. And now basically I'm also working on it within my function with Khalifa. It's the top ranked open source model. So what these models do is basically you take all the data, and I think you've been using these tools. You start interfacing basically with summarization capability, but also when you train them with data, well, they can solve some questions which are very specific to your domain. And typically, one of the things I'm going to show you is how we kickstarted some training on data related to 3GPP documents, and on which basically you can ask any kind of questions you would like to know on some kind of standardization effort that is being made, and you want to know some information, but also generate some code related to that. Within that realm, of course, of large language models, we have subsets which are what we call proprietary, and others which are research only, and others which are all commercial. What I want to advocate here is that open source models, and Falcon basically is one of them, are now having the same kind of capability as those property models that you have in the market. And what's good about open source is that you can take them, and for an industry like us, by fine-tuning them even in more data, you could build up basically some telecom GPT type of model on which all the community could play with. It would accelerate innovation, as you all know, and go forward. Next slide. Now, this, of course, comes with some numbers that these models are performing. Today, for information, we have benchmarks which are done for these models. And these benchmarks are mostly tailored with some basically evaluation benchmarks, which are mostly done in language. and in English being one of them. Typically, if you do Arabic, for example, we don't have those benchmarks. And this is how you rank these models, because they have to go through some tests and some ranking on what you have. So for example, if you want today to have a benchmark on models which are able to answer very specific questions in the telecom industry, we don't have them benchmark. It's by the way, a paper that I did with some of my colleagues is to start being able to evaluate how we can rank models which are now being used in the telecom industry and rank them. But just for information, we kickstarted that work, and Falcon, of course, was the open source model that we came up with, and on which the different benchmarks have been ranking it quite in the top manner. It doesn't contain telecom, because I told you we'll talk about it. It's more about fine-tuning, but it gives you a hint of this ranking, which you see every week, and which is quite interesting. Next slide, please. Now, when you build these models, of course, they don't come for free, okay? And they don't come for free. And since I'm in the ITU, I want to advocate, of course, two things. The fact that we want to become more and more inclusive and open source so that we can have all the people being able to use it. But we also need to think about the people who are working on this discipline and do not have the compute. So there's a very nice paper that I strongly encourage you to read. It's on Archive, called Survival Strategies for Depressed AI Academics. The abstract says the whole story about it. What does it say? Are you an AI researcher at an academic institution? Are you anxious you are not coping with the current pace of AI advancements? Do you feel you have no access to the computational human resources required for an AI research breakthrough? You're not alone. We feel the same way. A growing number of AI academics can no longer find the means and resources to compete at a global scale. This is a somewhat recent phenomenon, but an accelerating one, with private actors investing enormous compute resources into cutting-edge AI research. Here, we discuss what you can do to stay competitive while remaining an academic. We also briefly discuss what universities and the private sectors could do to improve the situation, if they are so inclined. This is not an exhaustive list of strategies, and you may not agree with all of them, but it serves to start a discussion. And so what the paper says is, of course, that academics should start looking at fundamental problems, more theoretical, because basically they don't have the resources. And here what I'm advocating is that, of course, we need to kickstart some activities altogether so that industry starts providing the compute power so that the smartest guys I know that I have seen so far, which are, of course, working in academia, can still thrive within their environment to build up basically the next generation telecom GPT that we're talking about. And by doing that, what we did, and when I was in charge at TII of the AI unit, is exactly start looking at how we could support basically academia by providing them the compute whenever they came up with very nice ideas to basically push the boundaries of these large language models. Next slide, please. And we made a call for that. It's in the next slide, in which basically we started basically to look at how we could build up, slide before, we could build up basically a community which basically could enhance Falcon with the capability of all the things that I'm telling about. And I think we need to push this idea much further in building an open source telecom alliance for basically generative AI, because of the large models that we're in a bit, with some objectives. These objectives are research and development, open source, promote the technology adoption of generative AI in our market, implementation and market adoption, having also an impact in standardization. I saw my previous colleague looking at the problems of AI and ML, but I think Gen AI, as you all know now, is getting in, being an innovation hub, and providing through that alliance some partners. TII is willing to do it, the access in computing and infrastructure, so that we can, on very, I would say, breakthrough ideas, push basically the Telecom GPT I would say, concept forward. Next slide. So if we decide to build such an open source model, and this is the kind of work that we're doing, what are we talking about? Well, we're talking about basically large language models which would have multimodal capabilities. And these large language models which have multimodal capabilities will be improving basically the end-to-end customer experience and basically also the end-to-end quality of experience that you have in the network. You start having images which are poured in, you have LiDARs, you have radio signals, you have cameras, and with all that, you can improve basically the classical things that my previous colleagues were showing, such as beam steering, power management, resource, coding, position. I'll give you a couple of examples on which we kickstarted our work on showcasing the capability of having all that data really as an input and being able to convert it into basically some streamlines in terms of improvement. But then there's a second thing that people are not seeing is that large language models or generative AI are not just here to improve the telecom market. There's also a whole breadth where the telecom industry, and especially 6G, has a big part to play in improving basically the large language model infrastructure. What we're seeing today is the fact that AI and generative AI is becoming more and more pervasive. We're having generative AI nearly at each point of the network. We're having it on a device, we're having it on the edge, we're having it on the fog, we're having on the core network. And the second tendency that we're saying is that these AIs want to talk to each other. It's not anymore a human talking with a ChatGPT, but a ChatGPT talking to another ChatGPT. We call this, by the way, agents. So you have an AI agent which is interacting with an AI agent. And of course, there's many, I would say, kind of challenges related to do that. The first thing is that whenever you want to have two AIs talking to each other, well, you need to build up basically the kind of protocols on which they're going to be talking to each other. Let me give you an example. If you want to send an image using this generative AI, you don't need any more to send the image. What you need to send is just the prompt, because from one side, if he has the model on the other side, you just need to know how to generate that model, that image or that video with the prompt, give that prompt on the other side, so you have huge compression rate, and he can generate that. And we know that large language models are typically super compressors. So what it gives you as an idea here is that, of course, there's a realm of looking at how you encode information and transmit information in a different manner that we used to do, taking into account, of course, the compression rate that is a dramatic increase in performance, but also the end-to-end latency that we telecom, I would say, manufacturers or researchers have to improve. Because, of course, whenever you want to do a generation of an image or a text, there's also basically some inference delay. And you need to take into account what we call the ultra-reliable low-latency communication aspect from an end-to-end perspective in this convergence of communication and compute. By the way, this idea of revisiting the way communication is made when you have not anymore people-to-people communicating, but AI to AI communicating goes within the realm of the concept, which I think, unfortunately, is still not well defined, called semantic communication. So you can look at these aspects. The other aspect also is that to make it ubiquitous, we have also a role in the telecom industry to make it basically a commodity. Making a commodity meaning bringing those large language models with billions of parameters to be able to run basically on devices, to be able to run on IoTs, and how we start playing in terms of configuring it, compressing it, quantizing this model so that we can have on each device that we're selling in the market this capability that we're talking about. This is, by the way, called on-device LLM, and it's continuing. The third aspect also where we have to play a role, and this kind of alliance is, I would say, a very good place for all the industry to interact and to start building, thinking, issuing white papers, pre-developing basically the ideas of standardization, and being able, of course, to pour on the academic world, which is in need of compute, by offering this capability of compute, is basically on how we leverage basically collective intelligence from this massive number of intelligence. What I'm talking about is intent-driven networks. What I'm talking about is basically auto GPT, all these ideas that you have an intent, you want to solve a problem, you leave all these LLM together or all these agents together, interact in the best way to solve your task in one way. So next slide, please. So let me give you a couple of examples of these two ideas on which we started with. So next slide, please. The first work we started had nothing to do with this LLM telecom or telecom for LLM. It started, of course, working on making these LLM work. I think I'm going to go very fast, but if you've never heard about LLM, just to give you an idea, these are large language models. They're a type of machine learning techniques that use natural language as input-output parameters, and they're trained on a various amounts of text. Next slide, please. And I told you, again, one of the big features about them and why people like them is that they are what we call few-shot learning, basically, type of models. So they can deal with unseen tasks on the fly, and at scale, this is extremely important. Next slide, please. Of course, these LLM outside the realm of telecom can do a lot of things. I won't go in detail, but one, of course, vertical that we're seeing today outside the telecom realm is what we call content creation with ID generation until game design. Next slide, please. It can go also to what we call sentiment analysis with text summary, video summary, visual analytics. Next slide, please. To also basically things which are goes to robot control, to chatbot, visual assistants, and other things like that, which are, by the way, today in the telecom industry already used more at the application layer. Next slide, please. And of course, what we're seeing in the market today is a subset of foundational models. I should add Falcon here, which is an open source one, where a lot of players are adding their apps through APIs. And these foundational models are like operating systems at the end. And of course, I think in the telecom market, we would need some kind of operating systems related to that. Next slide, please. So rapidly, if you never heard about large language models, just to give you a hint, why it has become so successful is that it all starts with what we call natural language processing. Natural language processing is about, of course, putting bag of words and trying to basically cluster them into things which are lookalike. And lookalike means in statistics mostly about correlating them. So a woman is a queen, a man is a king, and you go on like that. And NLP, unfortunately, had some caveats before 2017. Next slide, please. The caveat that they had is that basically they were based on some kind of architecture, RNN, LSTM, GRU, and these architecture had a lot of, I would say, drawbacks. They could not learn long dependencies. You know, when you use ChatGPT, you see the text, which is being very long. They fail long sentences, and they're mostly what we call sequential. Whereas you know that when you want to train a lot of data, you need something which is parallelizable. Next slides, please. And so in 2017, what happened is that some smart guys came up with a paper. The paper is quite known. I think by itself, it must have like 80,000 or 90,000 as of today, basically citations. It's called Attention is All You Need. And in that paper, the author came up with basically the idea of solving the two problems that I was talking about. The fact that you solve the long dependency problem and parallelization. And they came with an architecture which is at the heart of what we call the GPT architecture. In the T, it's called transformers, and the transformer was proposed in that paper. The G means generative, pre-trained transformer, which is at the heart of all the building of the models. Next slide, please. So now, how is this related to large language models before we get into the telecom? Well, basically, what do we mean by a large language model, or what does modeling language really mean? It's all about basically doing a approximation or learning what we call conditional distribution. So your goal when you're using these things is to predict the next word, the next sentence, the next image, and you go on like that. So in this example, you have here the capital of the United Arab Emirates is Abu, and you'd like basically to predict what's the X. So you'd like to know what is the property of X equal to Paris, knowing that the capital of the United Arab Emirates is Abu. What is the property that X is equal to Dhabi, knowing that the capital of the United Arab Emirates is Abu. And so at the end, what you want to do is learn that function. Learning that function is about projecting that function as a basis. You could, of course, project that function in a basis, which is a polynomial expansion, and say P of X is E0 plus A1X plus E2X squared, and you all go on like that, to a certain degree of the polynomial. The bigger your polynomial is, the more longer is your model. If you do that, you cannot come up with a technique, basically, which can learn all those weights in a very nice manner. It turns out, next slide, that if you want to do that, and it's the heart of all the systems that we're building, you need, first of all, to learn in a self-supervised way, so not basically label all the data. And you need basically hardware architecture to do it, so you have the hardware to do it, and which can learn fast. MLPFC is non-sequence aware. RNN, I told you, are not scalable. And it turns out that transformers is the exact way to be able to learn this property distribution, which will enable you basically to predict with a certain probability, because it's a probabilistic way, the next word, the next sentence, the next image. And then, of course, you're going to take the most likely in terms of probability to give the answer to the problem. Next slide, please. And so what we've been doing in TII, well, we started building, as I told you, these large language models just based on text only, and then looking at how we could basically then approach the problem of telecom. The first paper that we wrote was about understanding the large language models with the telecom data, in taking 3GPP documents, fine-tuning basically the model, and being able to see if we get accurate answers on the questions on OFDM, accurate answer that you want to get on CDMA, 3G, on asking basically some precision on, can I use Wi-Fi with this kind of protocol, and in which the machine will answer you and give you the kind of answer any kind of researcher or engineer in the telecom industry is requested. Next slide. So you can read the paper in detail. I'm going to give you two slides which express what I did. We started doing that, trained it, looking at the accuracy, and looking at how we could basically adapt pre-trained generative models which are existing and fine-tune to the classification and answers that I was talking about. Although, as I told you, benchmarking, evaluating how the model is good is still some work that can be done. There's a paper with colleagues that I did quite recently, which showcases that there and provides a benchmark. It's called QTEL, TelQTEL, and you can check it on arXiv. Next slide, please. Yeah, and you have here a case study also in terms of classification. Next slide. Now, let me give you two examples on the first idea that we talked about. You remember I talked about the multimodality. Well, multimodality is just about giving all the data in terms of images, RF signaling, and how you convert that into doing 3D imaging, how to convert that into doing wireless localization. Next slide, please. So we kickstarted that work. And you have to know that that work started with LLM for wireless imaging, in which we had the position signal and doing some kind of 3D reconstruction of the environment based on that kind of information. Next slide, please. We did also some LLM for beam management and showcase the improvement that you got with respect to the auto-encoder approach, with respect to the multi-model transformer. And here you have the kind of numbers that you get when you start taking more multimodality information, incorporating into basically that kind of T transformer of the GPT things. Next slide, please.
Just quickly, you've got a minute left.
I'll finish. This is the last slide. It's related to the Telecom for LLM. Next slide. I told you that one of the things, and I strongly encourage you to read our paper, is what I think the biggest impact of our industry, which is basically building the infrastructure of the future of the Internet of Intelligence. And building the infrastructure of the Internet of Intelligence is building basically the protocols on which these intelligence entities will start talking to each other, and how you leverage from this collective intelligence. It requires, of course, still a lot of work. It will have an impact, of course, on the self-design of networks. And for information, we tried, and it's the final slide, an example where we decided to look at the problem of how we could come up with an energy efficient reduction of our network by assigning some intent to some mobile phones, and they came up with a strategy on how basically they could reduce the energy consumption. You can see it in the next slide, and it's the final one. Next slide, please. The next slide gives you this example that we looked at, which we called multi-agent LLM game. It goes within the realm of multi-agent generative AI, and it's in that paper where you can look at the example that we give. I think I finished my talk, and I'm sorry that it took so much time to go through the slides, and I hope it was interesting.
Thank you so much, Mr. Deba. And it's really very interesting. And we have recognized that the Falcon is a very good, very powerful large language models. And thank you very much for bringing us through all the past, present, and the future of LLMs. And since we are running out of time, we can see if we have questions at the Q&A before the end of the session. Okay.
Okay, good.
Yeah, and thank you again for the interesting talk. And now let's move on to our next agenda. Our next speaker is Yuxuan Tan, and Yuxuan Tan received her master's degree in communication engineering from Fudan University, China. She is currently a 5G 6G researcher and research engineer at the R&D Center of ZTE Corporation and the State Key Laboratory of Mobile Network and Mobile Multimedia Technology, China. Her research interests include wireless communications and artificial intelligence. And her topic today will be a future evolution of wireless network for AI. Welcome, Tan.
Thank you. Thanks, Leah, for your introduction. Hello, everyone. I'm Tan Yuxuan from ZTE Corporation. It's my great pleasure to be the speaker for this AI for Good webinar to share our view on evolution to AI native 6G network. The title of my presentation is Future Evolution of Wireless Network for AI. So let's begin with the primary question. What is artificial intelligence? For human being, intelligence is the process of feeling, memorizing, recalling, reasoning, and action. Likewise, artificial intelligence refers to the cognitive capabilities of a machine, including analysis and decision based on certain calculation logic or knowledge learned from the data from the sensor. The results of such intelligence can be used to guide the policy execution of the system. The development of AI has experienced 4 stages. The first stage is the sprouting stage, and the mainstream at that time was the classical machine learning algorithms. The success of support vector machine and boosting algorithms was the combination of classic machine learning research based on human-designed features. However, although SVM can perform well in classifying data with complex distribution, it cannot even identify a cat in the picture, and that's when the deep learning began to sprout. In the second stage, AI technology was gradually getting mature. AlexNet turned out to prove the effectiveness of deep learning algorithms in feature extraction, and since then we have witnessed a great breakthrough in voice and video recognition, with an accuracy of 99% and 95% respectively. The generative adversarial network and adversarial attack have been proposed to generate new data with the same statistics as the training set, as Google started to work on autonomous driving. In the third stage, the astonishing performance of AlphaGo drew the attention of the whole world and drove the renaissance of reinforcement learning. At the same time, the basic abilities of reading, listening, and speaking based on deep learning are becoming mature and commercialized. In this period, not only AI algorithms are making great progress, the rapid development of chips, 5G, Internet of Things, autonomous driving, and some other new promising technologies also facilitate the further development of AI technology. Nowadays, with stronger computer power, more data, and more application scenarios, the AI technology is still in continuous booming. The release of ChatGPT, a dialogue robot program, has brought the large language model into people's sight and has become a new emerging machine learning paradigm. In a word, AI has integrated and profoundly changed our daily life, but its potential is still out there for us to further explore for a better life. Now let's return to the wireless network. What will it be with the assistance of AI? We think the future wireless network will be autonomous, predictive, on-demand, and smart operated with the introduction of AI. First, autonomous. For a long period of time in the future, the new generation networks will coexist with the previous generation networks. Also, even within the same generation of networks, the key performance indicators of network can change over time, which will bring great challenges to the operation and the maintenance of network. Take network optimization as an example. In the past, tasks such as network monitoring, anomaly detection, optimization, and problem solving have been carried out by human engineers. However, with the network parameters increase in the 5G era, the best solution cannot be reached by human anymore. We have to make our network autonomous in order to solve complex problems. Second, predictive. For example, we need to achieve intelligent traffic prediction in order to optimize the performance of the entire work. In different regions, there are different user preferences and different base station locations. Users in region A may prefer certain short video applications, while users in region B prefer to use the games or video sets. This will cause the traffic of each base station to vary. If there is an AI traffic prediction model, we can effectively judge the online behavior of network and predict the application services in a certain area, and then push the user's favorite content to the network node closest to him, which will greatly reduce network latency and improve user experience. Third, on demand. With the continuous development of technology, static network configuration can no longer satisfy the requirement of the network, and dynamic and automated policy has become a necessary capability of the network. On-demand refers to the system and the resources in a normal way at ordinary times, and automatically allocates additional resources when the system load begins to increase. Last, smart operated. In the scenario of customer service, traditional push systems will display relevant content or products based on users' requests, while active push system can actively push notifications, which will notify the users when the content is changed or updated, and make it more convenient for users to read and understand. Therefore, application of AI in operation can make marketing more precise. To integrate the AI machine learning techniques into the existing radio access network, the study item on AI machine learning enabled RAN was discussed in 3GPP working group, and the corresponding functional framework for RAN intelligence is agreed, which is comprised of 4 functional boxes, including data collection, model training, model inference, and actor. Data collection is a function that provides input data to model training and model inference functions, and model training is a function that performs AI machine learning model training, validation, and testing, which may generate model performance metrics as part of the model testing procedure. The model inference is a function that provides AI machine learning model inference output, such as predictions or decisions. An actor is a function that receives the output from the model inference function and triggers or performs corresponding actions. In addition, between these functional boxes, there are options like model deployment or update, model performance feedback, and feedback. The model deployment or update is used to initially deploy a trained, validated, and tested model, or to deliver and update the model to the model inference function. The operation of model performance feedback may be used for monitoring the performance of the AI machine learning models, and the operation of feedback is to feedback the information that may be needed to derive training data, inference data, or to monitor the performance of the AI machine learning model. For AI-assisted wireless network optimization, 3 use cases have been agreed as examples and have been discussed in normative phase of Release 18. The first one is network energy saving. The current energy saving schemes are vulnerable to potential issues such as inaccurate cell load prediction, conflicting targets between system performance and energy efficiency, rigid mechanism of conventional energy saving related parameters adjustment, and local improvement versus overall deterioration. Machine learning techniques can predict the energy efficiency and load status in the next period of the time, which can be used to make better decisions on the cell activation or deactivation to save energy. Based on the predicted load, the system can dynamically configure the energy saving strategy to keep a balance between system performance and energy efficiency and to reduce the overall energy consumption. The second use case is mobility optimization. The machine learning techniques can be used for reduction of the probability of unintended events, UE location or mobility or performance prediction, and the traffic steering, thus enhancing the mobility management. The third use case is load balancing. Load balancing decisions relying on the current or past state cell load status are insufficient, and it's difficult to guarantee the overall network and service performance when performing load balancing. The solutions based on AI machine learning model could be introduced to improve the load balancing performance. Based on collection of various measurements and feedbacks from UEs and network nodes, historical data, the AI machine learning model-based solution and predict load could improve load balancing performance in order to provide higher quality user experience and to improve the capacity of the system. Here we take the network energy saving as an example to show the effectiveness of AI machine learning technology. The machine learning algorithms can predict the energy efficiency and the load state of the next period, and based on the predicted load, the system can dynamically configure the energy saving strategy to keep a balance between the energy efficiency and system performance and to reduce the energy consumption. Since typical energy saving strategies used for wireless networks including symbol shutdown, channel shutdown, carrier shutdown, and deep sleep, and different strategies on different granularity will produce different energy saving results. The machine learning algorithms can proactively identify the energy saving scenarios and decide which model is more suitable for a certain scenario. Pictures on the right respectively show the average power supply and energy efficiency without energy saving strategy, with traditional energy saving strategy, and with AI machine learning based energy saving strategy. It can be seen that the use of AI machine learning techniques results in a reduction of 23.87% in power supply and an improvement of 23.4% in energy efficiency. This page is an example of AI-based 5G energy saving in Thailand under the cooperation of ZTE and AIS. With the AI-based energy saving strategy, the average consumption is reduced by 25.97%. Each AAU will save about 368 bahts per month, and for the chill area, it will save about 10,672 bahts per month. To support AI function, 5G networks present functional models to monitor and enhance the performance, and each AI function is deployed in a single node to perform intelligent network optimization decision, regardless the AI machine learning capabilities of other nodes. However, in the future wireless network aiming at self-sensing, self-learning, self-decision, and self-evolution, New features such as intelligent data perception, intelligent modeling, intelligent monitoring, and distributed learning architectures are needed to support these self-capabilities and realize the integration of AI, machine learning, and communication network. In addition, the future wireless network will be a multi-node collaborative intelligent cluster. Namely, multiple devices from an intelligent cluster cooperate with each other to achieve AI machine learning functions dynamically, thus effectively utilizing the computer power of each node and each network element. In this page, I will give an introduction to the Nanjing Binjiang manufacturing base of ZTE. In this park, we managed to use the latest 5G technology to fully cover the administrative and the factory areas. The AI technology is used to automate and intelligentize each unit. Funa is ZTE's most intelligent factory and one of the most advanced parks in China's communications manufacturing industry. The park is equipped with some of the most advanced technologies. The cloud AGV is used for intelligent collaborative scheduling, and machine vision is used for timely detection of potential safety hazards, device quality inspection, and automated assembly line. The intelligent analysis tools are provided for comprehensive monitoring of assets, energy consumption, and environment, and intelligent prediction plays an important role in predictive management of quality, contract, and logistics. By integrating the advanced digital techniques like 5G, digital twin, artificial intelligence, and big data deeply with the traditional industry, this global smart manufacturing base has achieved significant progresses in production efficiency improvement, cost reduction, and green energy saving, which is a successful practice of 5G and artificial intelligence. Based on the different requirements of different tasks, task-driven cooperative intelligent cluster needs to be dynamically created and intelligently managed. Multiple types of devices need to cooperate to complete the required tasks due to the limited capability of a single type of device. The picture on the right is an example of inspection on task in smart factory by using the task-driven cooperative intelligent cluster. The UAV, auto-drive vehicle, and the camera device are grouped as a work group to perform inspection tasks in smart factory, and the auto-drive vehicle is selected as head, which is responsible to distribute the subtasks to members in this work group. Since the cluster management is dynamic, the change of head, the addition or removal of member are allowed under the control of network. Different cluster members can be allocated with different subtasks and configured with different transmission paths considering the capability distinction of members and radio quality. The flexible data offloading within the work group is allowed. The cost management, including cost monitoring, environment, and prediction, is in task level, and the performance requirements and results per task level can be achieved. The task cooperative intelligent cluster has three characteristics: task-driven, cooperative, and intelligent. Task-driven means that there are different requirements for different tasks, so various types of devices can be selected, and the cost management is in task level. The selected multiple types of devices are cooperative to complete the required tasks due to the limited capability of a single type of devices. Among them, the head acts as a control node, and the members perform its own subtasks cooperatively. As an intelligent system, the CIC can realize dynamic head selection and member management, intelligent subtask allocation among members, and on-demand data transmission path termination. Currently, the 5G network is a service-based architecture, providing a modular framework for meeting stringent latency and reliability requirements. However, it's far from enough to make the network intelligence by only introducing the AI technology to solve a certain network optimization problem. The continuous changes in radio environment require to retrain and update the fixed machine learning models, resulting in the repetitive work and hindering the intelligence of the wireless system. Therefore, the future wireless network is expected to be an AI-native architecture, which not only apply AI to enhance a certain function, but integrate AI into every aspect of wireless communication system to depict the vision of intrinsic AI. Here we propose 3 potential application scenarios in the future 6G AI-native network. The first one is intelligent sensing and cooperation. The AI technology is important in achieving accurate sensing in complex environments. Due to the limited information in a single wireless signal, collaborative processing of multi-mode, multi-user, and multi-scenario signal is a critical guarantee of high-quality sensing. Specifically, collaborative learning of multi-mode signals facilitates multidimensional and multi-granularity sensing for targets. Combining observations from users at different positions makes target reconstruction closer to reality than using only a single user signal. Information interaction between multiple base stations helps large-scale environment reconstruction and high-quality sensing. The second one is intelligence-assisted digital twin. It requires the next generation wireless network to provide comprehensive support for the real-time reaction in virtual world, the mapping in real world, and the information interaction between the virtual and the real world. Specifically, an intelligent machine that can simulate wireless state from multiple users and scenarios in virtual world is necessary. Meanwhile, the capabilities of autonomously making decisions and adjustments after obtaining simulation results from the virtual world is also required. In addition, it's also valuable to provide high-efficiency transmission for the interaction between virtual world and real world, including information compression and encryption. The third one is intelligence towards semantic communication. Integrating user requirements and known information into the communication process is the fundamental principle of semantic communication. Analyzing users' wireless state and accordingly formulates the transmission or decoding methods to constitute semantic level communication at the physical network. At the physical layer is an essential function. For widely used semantic level communication over the whole 6G network, such functionality will have to be achieved across multiple users and multiple scenarios. In addition, to intelligently couple with diverse knowledge bases, a sufficient amount of information capacity and intelligence level for wireless model is also necessary. In summary, in the AI-native 6G network, the seamless integration of artificial intelligence into 6G network can realize intelligent interaction and collaboration from multiple users, multiple scenarios, and multiple functions for these advanced applications, leading to a better life for all humanity all over the world. That's all for my presentation. Thanks for your watching.
Thank you very much for the interesting presentation, and it's great to show that how to use AI for network and how to use the network for AI, and the potential AI native scenarios in 6G network is very useful. And thank you again for your great presentation. And then let's welcome our next speaker, Vishnu Ram. Vishnu is currently an independent consultant, and he is a vice chair of ITU Focus Group on Autonomous Network, and also he is the co-convener of ITU Correspondence Group on Datasets. Previously, he was a co-editor of ITU Focus Group specifications on machine learning 5G. And he is very experienced in today's topic, AI native 6G. So let's welcome Vishnu Ram with his topic, Experiments Towards Building Native AI XG Networks. Vishnu, over to you.
Thank you very much, Leah. And it's a great pleasure to be here. Actually, so far we have had excellent talks. Thank you very much for for those talks as well. Today, I will go over these experiments towards building native AI in next generation networks. So this is a rough compilation of experiments, okay? So why do we need these experiments? There are several ideas which are thrown around as part of 6G, as part of AI native applications of AI, and so on. So we have to figure out which ideas will be picked up in the next G, and also which ideas have to wait. I mean, I have to say some of these ideas are mine. So I understand the pain, but there is only so much that is going to go in, and some of them have to wait. As Shafong correctly mentioned in the beginning, remember? So there is a trade-off that one needs to look at in terms of benefits, and that's what determines. Well, if you look at the list, the previous speaker talked about, right? You can see that there is AI native, which is really a hot keyword. There is digital twinning, massive twinning, federated learning. A couple of speakers talked about integrated sensing, adaptive networks, service-based architectures also was mentioned, and layer-wise end-to-end system architectures. You can see this in the literature survey. If you do a quick literature survey in this topic, you can come across this list. So today, as Leah mentioned, I have been forced to look at that. I've been forced to look at some of these technologies, and I will compile and summarize what are the basic experiments that I myself am planning, and as well as some of our partners are planning as well. Some of our partners are currently doing as well. So first experiment is that of a disappearing network. So what is a disappearing network? I will explain in a bit. Then second experiment is something like a weight training, what one's do to build up our muscles, no? Third one is to serve generative AI. That means to provide it as a service. Fourth one, what I call is to be human in the sense that to serve humans. That's the fourth one. And finally, I also look at how to model these network functions, to be a little bit more practical and how to model these network functions. So then let's jump into the first experiment. The first experiment is about disappearing network. No, I mean a little bit of magic, but yeah. So I have divided this slide into three parts. First one on the steps in the experiment. Second one on the aims of the experiment, and finally, I want to make sure that I'm not going crazy. There is a sanity check which we have done as part of the literature survey. So that's what I will talk about. Just to give you an idea that it's possible to be done if you extrapolate it a little bit. What are the steps in this experiment? So first of all, we would think that we are able to discover and understand the new use cases and trends. You heard about several of these potential experiments, use cases that today. Remember? So Shafang talked about it, as well as Rohan talked about it, as well as Yushwan talked about it. So there are several of these use cases. But how does these use cases come about? Who made these use cases? These are human-made, potentially looking at what are the data which comes to form these AI models as part of this use case, then studying that, implementing that, modeling that, and so on. But the question is that can you as a next step discover and understand some of these use case trends, use cases, and discover this collection of use cases, group of use cases, generate these AI-driven pipelines, which can be done, but at the same time, applying some of these concepts that Nirwan talked about as well. So then, chain and create this hierarchy of AI pipelines. That gives us the ability to build complex pipelines, and then shift this compute from real-time to non-real-time, and shift the latency as well from real-time to non-real-time. These are the steps in this experiment. Why do we do this? What's the aim of this experiment? First of all, we would like to give more autonomy to the network in the sense that level of autonomy goes up. Bringing the focus, user experience in the focus, you are able to make sense of the environment with the sensing, for example, integrated sensing, and then specifying specifications for fine-tuned models that gives us customization abilities. Right now, we look at some extensions, some vendor-specific extensions, but this one is about fine-tuning abilities as well. Build and extend the existing pipelines and take advantage of the AI-driven potential background tasks that are possible, which are AI-driven. At the moment, there are some tasks that we heard today, some use cases that we heard today as well. Just doing a sanity check. The 3061, y.3061, that there is, I have it in the references at the end. But basically, it's an architecture framework on autonomous networks, which is a work of ITUT that already talked about evolution and experimentation of controllers. Looking at one small part of it, this doesn't cover the entire use case, but one small part of it. Our background work, 3172, which ZTE, Leah was a great part of it as well. So 3172 looks at machine learning pipelines and flexible. It already talks about flexible chaining of machine learning functionalities, maybe 4 years back, or so I don't remember when we published it, must be 4 years back. But at that time itself, we looked at some of these technologies. And there is a ZTE white paper, I have it, which also talks about the shifting of delays, latencies from functionalities into real-time, non-real-time. Some of these tools and techniques where to hide the network is that basically that you look at, this framework from y.3172. You can see this framework there. Some of you would be already familiar with it, but we have this sandbox function and the underlay function. That's the basic part of this. The top rectangle that you see here and the bottom rectangle that you see here. And then what we are looking at right now is to drive this sandbox, which does experimentation using AI-driven technologies. We also look at this orchestrator on one side, which manages this functionality, MLOps types management. There we have continuum orchestration is the current hot topic, which is introduced by Hexa. So yeah, so we look at 3172, which gives us this layered functionality, and the 3061 extends it a little bit to introduce autonomy in the network. Some of the metrics and studies. First one is in network creation of AI models. There we look at distance between the sandbox and inference. Distance in the sense a logical distance, and management of this life cycle of AI models that we measure level of autonomy, inter-domain chaining, which looks at ops and pipeline node distance, model customization, which looks at steps in fine-tuning, and model management, which looks at, and knowledge base, which looks at performance of discovery and prediction, how well we are able to predict the use cases. Remember what I talked about, predicting and inferring the use cases, discovering the use cases themselves. Now we come to weight training. Weight training is very important, as you know. The steps in this particular one is that we transfer data. Right now, we look at networks for transferring data, right? But now in this experiment, we would like to transfer model weights. So that's the only difference. And transferring models becomes transfer of learning, transfer learning techniques, message extensions. Right now, if you implement protocols, we would implement parsing of message extensions. That becomes as fine-tuning aspects. State machines and logic becomes models. That's how we experiment with this kind of weights training. And programmable protocol stack, you see this in many of this literature. We would like to look at it from the form of model-based interfaces. What are the aims of this particular experiment? We would look at distributed training and inference. I think we heard this today with the previous speakers, but also AI native implementation of functions in the network is not only pervasive use of AI, as Yushan talked about, but also implementing the functions in the network as AI functions, models. Architecture options are generated, taking advantage of potential cloud-native softwareization, just building on top of it, and allowing regional knowledge bases and customizations so that we can train models based on it. A quick sanity check here. Microservices are already talked about. Exchanging model parameters are already talked about. Signaling between them is also talked about. Change from session-oriented communication to AI task-oriented communication is also talked about in the literature. So this is a quick tools and techniques, which includes weights for this weights training. We start with the knowledge base, top to bottom. We train models based on it, derive different architecture options, which allow us to implement use cases. And on the right side, we have vendor-specific extensions from this knowledge base, regional customizations, and deployment options which come out of this. This forms a totally AI-native approach for us. What are the metrics and studies? AI customizations across network domains, we can look at validity of generated options, whether the architecture options are indeed valid or not, right? And then the impact of network KPIs. I think my colleague talked about it in the beginning. Shafan talked about it. That there is some of the use cases are not accepted at all because of this particular factor, right? So we don't want to there. So we want to make sure that time-based quantized impact metrics are indeed covered here. The nativeness of AI. So the nativeness of AI we have to look at in terms of integration effort of AI pipelines in network functions. And knowledge management itself, we're looking at validity of knowledge captured in the knowledge base. There is a definition of this in Y.3061. You can look at it. Generalization and relevance of knowledge base also we look at in terms of studying and measuring considerations. Next experiment, which I would suggest, is serving generative AI. And in this experiment, these are the steps. So first, the network serve out generative AI as a service. I think you heard AI as a service, but here we are looking at generative AI as a service to enable new applications. And if you look at the current model, there is the sensing modeling based on that sensor sensed data, infer based on that, and then trigger an actuator, right? That's this typical pipeline that one would follow. Study that and then look at the right side. Welcome to that. Enabling the AI that will slowly morph towards embedded AI, built with AI and enabled using AI with some regional customizations. So what are the aims of this experiment? We want to take advantage of signal processing, applies to, that includes generative AI signal processing pipeline. Signal processing, generative AI, signal processing. That's the pipeline that we would like to look at. And what are the applications of this technique to different planes? Control plane, user plane, management plane. Then try suitably tuned multi-model large networks. I think you heard it today from Marwan. Semantic communications, I think Marwan mentioned this as well. How to apply this concept, we have had some discussions in ITU previously regarding this. Sanity check. So sanity check, AI native applications are talked about in the white paper. I have it at the end, already referred. NGMN talked about this distributed learning inference, and this semantic communications aspect was also covered in one of our contributions in ITU. Some tools and techniques which we are already doing, we created a graph-based knowledge base as part of this experiment. And we use this in combination with the network simulator. We are now focusing on creating this generative model on top of this graph-based knowledge base, using this as a training factor, fine-tuning factor for us. Y.3061 includes an architecture picture that you see here, which has this basic concept, but with respect to autonomous networks, autonomy in mind. So we have this framework with that in mind. So you have knowledge-based autonomy engine and the rest of the network along with an orchestrator. That forms the basic framework introduced by Y.3061. We are extending that a little bit so that you can generalize it to create this serving of this generative AI based on knowledge base. That's what we're trying. ITU is actually conducting a build-a-thon. It's similar to a hackathon, but here we are using this generative AI framework to enable participants to not only add knowledge based on this graph knowledge base, but also to utilize this to create new applications, use cases, which are based on a specific domain. If you are interested, you can look at this website. Some of the tools and techniques, we look at a specific set of use cases to train this knowledge base, add to this knowledge base, architectures are based on that, open codes are based on that. Then, I mean, when I say that, that means use case. So if you look at a set of use cases based on autonomous networks, can we create a knowledge base based for that? And then we can expand that to open it up so that the served generative AI can be utilized using a chatbot. This is the point that I'm trying to look at in this particular slide. And this is currently ongoing work as part of this build-a-thon. Everyone talked about the problems, depression. So we have the medicine. So the ITU provides state-of-the-art compute platform for our challenge participants. There is free GPU access in case there is a challenge link at the end. At the bottom. If you are registered for this challenge, we give free GPUs. So what are the metrics for this particular serving generative AI? We would like to look at validity or loss of information, applicability to verticals, and algorithmic cost, as it includes complexity, data, compute cost, and so on, as part of this particular generative AI study. The experiment 4 is to be human. So what are these experiments? Steps. First is to understand the human. This could be done using interfaces, sensors, chatbots, multimodal data, whatever you heard today, but with the purpose of understanding. Then to make the human understand, that's a tough job. So, you look at how to make this haptics emoticons to play so that you can make the human understand what the machine is talking about or the network is talking about. How to learn some specific preferences, for example, dialects, accents, whatever. So that is the aim of this experiment is to use semantic awareness, sensing to provide a humane interface. Collaborative design, continuous evolution is talked about. I will come to that in a bit. And then going beyond the current level of intent-based approaches. I think you heard intent-based approaches today. We would like to go beyond that a little bit and study these areas with some experiments. Quick sanity check. You can see that Qualcomm is already talking about the white paper that algorithms are semantic aware of data source can improve system performance and so on. And then there is perception, meaningful for perception and preserving source information as part of metadata helps. Intelligent co-design, prediction, co-design, sensing is talked about by NGMN, as well as ability to deliver information related to human senses and so on. Then the last experiment is to model the network functions. The steps in this experiment are the placement. Function placement becomes model placement for us. That is an important part. And then we would like to also look at function placement becomes pipeline placement for us, supporting different topologies, that means network topologies. And then architecture optimizations as well. What are the aims of this experiment? It's important to ITU, no? So role of standards, how the standards are impacted by data pipelines, model pipelines, and what does the network provide for supporting this new type of network functions which has AI in its DNA? Which features are packaged as models, whereas which features are packaged as, let's call it, legacy network functions. The sanity check is, there are a bunch of sanity checks here, which includes ZTE as well. That is, there is a nice ZTE white paper which talks about feasibility of native AI for a given use case, depends on location of data to train the AI model and so on. That's already talked about. There is a complete procedure call from Hexa, which the group together to form self-contained procedure-based network functions. And streamlined network function interfaces and interactions are talked about as well. Leah talked about correspondence groups. We have a correspondence group which works on this particular aspect. There is a meeting list and there are bi-weekly meetings. There is one actually tomorrow. And my colleague will chair that meeting as well. So please, this one runs till March 2024. If you are interested in any of these studies to exchange various viewpoints and related supporting material, etc., this is the place. There's a bunch of references. With that, I believe I am on time. Thank you very much, and back to you, Leah.
Thank you so much, Vishnu, for your sharing from the for your sharing your experience on possible ways towards AI native networks from the view of experiments. It's very informative. And we also welcome everyone to join our session tomorrow about the AI 6G corresponding group. And now I think we've concluded all the talkings. And is there any questions from the audience, Julian?
Nothing yet.
Okay, yeah, maybe we can have some discussions within the speakers. First, we have Vishnu to ask Xiaofeng about the 3GPP progress on LLMs. Xiaofeng, could you please answer this question?
Yes, I think I have provide some answers in the box, and I think right now in 3GPP is still think about the use case levels specification works, and maybe in the future LLM should be discussed in maybe at least in release 20, I think. But in release 19, I think the LLM concept is not present by any companies, and so I think there's maybe still some time we should study more. Yeah.
Yeah, thank you. I also think that LLM studies in the telecommunication is in very early stage. But actually, two speakers, Vishnu and Marona, both talked about this. Both talked about LLMs in the telecommunication networks. So, Vishnu, could you please elaborate what LLMs could actually do in the telecommunications networks, and what are the challenges, if you can elaborate? Thank you.
Yeah, thank you, Leah. That's a great question. In fact, if you look at Yushuan's presentation today, she presented a bunch of use cases as well as the pipelines or models which goes a long way, right? So to me, there are two types of possibilities. One which does not use any large models or generative AI or anything like that. It just uses 3172 based pipelines, and then that's enough for those use cases, for example, right? And then there are some use cases which requires large models. For example, the ones which Marwan talked about. There are some use cases which requires, for example, a log parsing. The logs which comes out of the networks, they need to be parsed, and some questions need to be answered. Maybe root cause analysis has to be done. You can do it in combination with the code, and with this multi-mode data and multi-mode models, you are able to do this in really easily when compared to normal 3172 based pipelines. So there are two classes of use cases here. One which does not require any large models, and the other which really helps us if you have multimodal data and large language models. Now, Xiaofeng says that, in fact, Xiaofeng's reply is only to me. So Xiaofeng says that it is it is still in early stage, and that is true. Actually, in 3GPP, it is still in early stage, and they look at how to integrate this into the network, and that's very important that we look at performance before integrating. Thank you.
Thank you. Thank you very much. And also, I have a question to Yuxuan. Yuxuan, so you talked many scenarios of AI in 6G, and could you please elaborate or summarize what's the key difference between using AI in 5G and using AI in 6G? Thank you.
Thank you, Leah. The 5G network is a service-based architecture, and it provides a modular framework for meeting some requirements. So it just used the AI technology in a single node, and regardless of the AI machine learning capabilities of other nodes. But for the 6G network, it is expected to be an AI native architecture. So it will use the AI technology into every aspect of the system to depict the vision of intrinsic AI.
Thank you very much. So that's all questions from my side. Any other discussions that we need to talk about from other speakers? If no, maybe we can conclude all of our presentations and Q&As today. And thank you all to the speakers for sharing your knowledge and perspectives on
Leah?
AI native 6G. Yeah?
Yeah, we just have one more question.
Yeah.
For a second.
Yeah, I see. Okay, that's a long question.
Yes.
So yeah, it's for Dr. Xiaofeng Liu. So has 3GPP started? Is this the correct question from Vishnu?
Yes.
Yeah. I just summarized the discussion. So if we have Xiaofeng's permission, we can post it for others. Actually, his answer is very comprehensive and it's very informative. Thank you.
Thank you.
Yes, you appreciate for the proposal, and I'm fine to put this for the to the network or share to anyone who would like to think. Yeah.
Thank you, Xiaofeng.
Yeah, maybe we can also have more offline discussions after our session today. And once again, my appreciation to all the speakers and to all of you for joining. With that, we will come to the end of our today's session. So thank you and goodbye.
Thank you. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Thank you.